Welcome to today's lesson. Today we will use the discriminant for a quadratic function, and we will be able to explain the importance of finding the discriminant of a quadratic function. So let's take a look at today's lesson. Let's take a look at today's do now. Solve the following inequality. For your inequality, you have 1 less than negative times x plus 3 squared. I am going to include minus x at the end because I forgot. And now you can pause this video, try this out, and we will compare our answers. Alright, so here is my process for solving this inequality. I reversed the x squared piece to be on the left. That's just my preference. I distributed that squared, distributed the -1, moved that one over, combined my like terms, and then I factored. I factored out the GCF, and I got my two factors of x plus 5, x plus 2. Which gives me my two roots of x equals -5 and x equals -2. Since we are dealing with an inequality, I graphed it on my number line. I did my test points, so I chose -6, plugged that into the original function, got a false statement, did -1, got a false statement, which told me that the solutions fall between -5 and -2. I wrote my solution using a compound inequality. So we're talking about -5 is less than x, which is less than -2. Less than only, not less than or equal to, because our inequality was a less than symbol. So let's take a look at today's thinking. How do we use the discriminant to help us find the roots a quadratic contains? The discriminant. The discriminant gives us information about the roots of a polynomial. We used the formula b squared minus 4ac. This piece is what is under the radical for your quadratic formula. We are only worried about what's under the radical. We do not include the radical when we are dealing with the discriminant. So how do we use the discriminant? We have three possible cases. The first case we have is I have a parabola in which I only have one root, one real root. If I have one real root, I could obviously look at the graph, but I can take a close look at the discriminant. If I do b squared minus 4ac for that quadratic, and if it is equal to 0, that means that I have one real root. Sometimes you will see two equal roots. Why two equal roots? Because we are dealing with a quadratic, and a quadratic's exponent is 2, meaning there's always two solutions. So in this case, there'll be two equal solutions. The next case we can have is we have a quadratic in which it intersects the x-axis in two places, which means we have two real roots. How can we use the discriminant? We will look at the discriminant, b squared minus 4ac, and if we have the discriminant is greater than 0, that means that we're going to have two distinct roots. The third case, we are looking at a parabola in which it does not touch the x-axis. Here we would have no real roots. We would actually have imaginary roots here. If we look at the discriminant, b squared minus 4ac, and we have the discriminant is less than 0, that means that we are dealing with imaginary roots. Think about this. Why? Because we are dealing with the quadratic formula piece. So if I were to do the square root of any negative number, I would have imaginary roots. If that square root piece would be negative, we would have imaginary roots. Let's take a look at our first example. We have determining the number of solutions a quadratic function has. How many real solutions are there for the following functions? We have a, which is f of x is equal to x squared plus 3. What we are going to identify are our a value, b value, and c value. And those values come from our quadratic written in standard form. The next thing that we're going to do is write down our discriminant. And we are trying to find how many real roots we have. So we're going to work with that discriminant and then compare it to 0. So let's plug in our B, our A, and our C. So negative 12 is our discriminant piece. What I'm going to determine is this equal to 0? Obviously not, which means that we don't have one real root. Is this greater than 0? Obviously not, which means we do not have two real roots. This discriminant is less than 0, which is telling me we have no real roots. This case would lead us to imaginary roots. Again, not a focus in our class. Part B, we have the function f of x equals 2x squared minus 4x minus 3. We're going to do the same thing. We're going to identify our a, b, and c values. Once I identify my values, I'm going to start off by writing my discriminant. I'm going to plug in the b, the a, and the c value within my formula. And we're going to evaluate. And we get 40. So is 40 equal to 0? No, 40 is a value that is greater than 0, which is telling me I have two real roots, two real distinct roots. Let's take a look at our next problem here. Number 2, let f of x equal 3kx squared plus 2x plus k. We want to find the value of k if the function has two equal roots. If a function has two equal roots, what does that tell us about the discriminant? That tells us that b squared minus 4ac is equal to 0. So I have to use that fact. What I'm going to do is I'm going to identify the value of a, b, and c as I did before. So the value of a in this case would be 3k. The value of b would be positive 2, and the value of c would be a positive k. So we're going to plug this into our formula. That's my discriminant, and it is equal to 0. Why is it equal to 0 again? Because we have two equal roots. So we're going to evaluate this. And our goal is to solve for k. So I'm going to isolate k and see what we get. I get k squared equals 1/3. I'm going to square root both sides. And again, the square root of any number is always positive and negative. We get k is equal to positive and negative square root of 1 over square root of 3. Can you simplify anything? You must. And we have positive and negative 1 radical 3. Now, we do not like radicals in the bottom, so we are going to rationalize this, which just means we're going to multiply by radical 3 over radical 3, which would give us our k value of positive and negative 1 times radical 3 for the numerator. And in the denominator, we have radical 3 times radical 3, which would equal radical 9, which is a perfect square. So that would give us our positive 3. And the k value could be either a positive radical 3 over 3 or a negative radical 3 over 3. That is all we are finding. We are just finding the value of k. One more. Let f of x equal 2x squared minus 6x plus k. Find the values of k in each case below. So we have the first case. F of x is equal to 0 has exactly 1 root. If I have exactly 1 root or 2 equal roots, what does that mean? That means that the discriminant is equal to 0. So we're going to identify the value of a, b, and c for our specific function. So the value of a is 2, b is negative 6, and c is a positive k. And similar to the question above, we are just going to be solving for k. And we get k is equal to 4.5, or the equivalent fraction. Part B, we want to determine if f of x is equal to 0 if we have exactly 2 roots. What does that mean? That means that we have 2 distinct roots, 2 different roots, which means that the discriminant is going to be greater than 0. So let's plug in the value of b, a, and c and evaluate for k. And we get very similar numbers, right? Because we are dealing with the same a, b, and c value. If the k value is less than 4.5, so let's say k is equal to 4, this case would occur. Part C, if f of x is equal to 0 and we have no real roots, which means that the discriminant is going to be set less than 0. So we're going to plug in as I did before. And we get k is greater than 4.5. So if we were to plug in, let's say a value of 5, right, because 5 is greater than 4.5, into our function, we would have no real roots. We would have imaginary roots. So for part D, f of x is equal to 0 has real roots. So in how many places can we have real roots? We could have real roots if my problem is k is equal to 4.5, so we have an equal situation, or if I have a less than 4.5 situation. So for part D, we're kind of merging those two together. K has to be less than or equal to 4.5. In both these cases, we have real roots. For part E, we are dealing with f of x is greater than 0 for any x value that is an element of the reals. So for part E, all we're really doing is looking at the discriminant and just setting it greater than 0. And that would be our answer. For part F, pretty similar. we're going to be dealing with f of x is greater than or equal to 0 for any x value which is an element of the reals. We are going to be looking at the discriminant, setting it greater than or equal to 0. If we plug in the value of b, a, and c for part E and F, we'll get very similar results. So I will just give you the results for each since we did the work already. So here for part E, it's going to be similar to that part B, giving us our k value that is less than 4.5. For part F, it's going to be similar to part D because it's a greater than or equal to, right? We merge parts A and B together, which would give us our k value, which is less than or equal to 4.5. So we use the discriminant to tell us how many roots our quadratic has: one real root, two real roots, or no real roots. We use the discriminant to help us find missing values within the function. And that is all for today's lesson. So keep learning, keep growing, and I will see you in our next video.